Let's go step by step through how to do a redox balancing for acidic conditions. The first thing is we have to take a look at our redox equation and identify the individual oxidation state or oxidation number for each element in the equation. For this equation, using our oxidation state guidelines, we have some things such as the chloride ion, which is a monatomic ion, so the oxidation state is the same as the charge on the ion. For our chloride, its oxidation state is -1. Likewise, for our chromium 3+ ion, its oxidation state is +3. And then our elemental chlorine, all elements in our naturally occurring state have an oxidation state of 0. With the dichromate ion, oxygen in compounds has an oxidation state of -2. That gives us a total from the oxygen of -14. The ion has a charge of -2. The oxidation states need to add up to -2. That means the oxidation state from the two chromiums is a +12. Individually then, the chromium has an oxidation state of +6. We've now identified the oxidation state for each individual element. Our next step is to see what changes take place between reactant to product in the oxidation state for any of our elements. Looking at the oxidation state, we can see an individual chromium has changed from +6 as a reactant to a +3 as a product. This is a decrease in the oxidation state, which is an indication that this is the process of reduction when the oxidation state goes down from reactant to product. If we look at our chloride ion, chloride starts out with an oxidation state of -1, ends up at 0. This is an increase in oxidation state for the chloride. An increase in oxidation state identifies the process as an oxidation process taking place when the oxidation state goes up from reactant to product. Now that we've identified our oxidation and reduction half reactions, our next step is to split the reactions into separate half reactions, one representing oxidation, one representing the process of reduction. What we've now done is separated our half reactions so that we have our reduction half reaction, which was identified by seeing that the oxidation state of chromium went down from +6 to +3 in this process. We've separated that from the oxidation half reaction, which we identified by seeing that the oxidation state of the chloride ion went from -1 up to 0, an increase in the oxidation state to identify the process as oxidation. The next step in our strategy is to balance the actual elements that are being oxidized or reduced first. The first atoms to balance, again, are those being oxidized or reduced. This is a key step. To balance the chromium atoms, we need to add in a 2 in front of the Cr3+. To balance the chlorines, we also need to put a 2 in front of the Cl-. This is a key step in the process. This must be done first when doing oxidation reduction balancings. Always remember, identify, and then balance the actual atoms being oxidized or reduced first. The next step in the strategy, now that we've balanced the actual atoms being oxidized or reduced, is to balance the oxygen atoms that may appear in either half reaction by adding water to the equation. We can add in water molecules because these are aqueous systems and they're surrounded by water molecules, so water molecules are readily available to participate in the reaction. If we notice in the reduction half reaction, the dichromate ion contains 7 oxygen atoms, which we need to balance. We balance this out by adding 7 H2O molecules to the opposite side of the equation. The 7 H2O molecules add in 7 oxygen atoms to balance the equation. In our oxidation half reaction, we do not need to add any water molecules because no oxygen atoms appear in the oxidation half reaction. Our next step is to balance out the hydrogen atoms by adding in H plus ions to whichever side of the equation needs hydrogens to balance the equation. We can add in H plus ions because the solution is acidic, and an acidic solution has an excess of H plus ions present in the solution. When we look at the reduction half reaction, we added in 7 water molecules, which has 14 hydrogen atoms. To balance this out, we're going to put 14 H plus ions on the opposite side of the equation to balance the hydrogen atoms. By placing the 14 H plus ions over here, we've balanced our hydrogen atoms and we're ready to move on to the next step in the strategy. Now that we've added in the hydrogen atoms, our next step is going to be to balance the charge in our half reactions by adding electrons to the appropriate side of each half reaction. What we want to achieve is make sure that each half reaction has the same charge on each side of the reaction. For example, 2 chloride ions here have a total charge of -2. The elemental chlorine has a charge of 0. We want to have each side have the same charge, so what we add is 2 negatively charged electrons to the right-hand side, and that gives the right-hand side a charge now of -2, and our charge in this half reaction is balanced with -2 on each side of the half reaction. Looking at the other half reaction for reduction, we have 14 plus 1s from the H plus ions, and we have -2 from the dichromate ion. This gives us a total charge of +12 on the left side of the half reaction. The 2 chromium 3 plus ions give us a charge of +6. We want to balance out the charge. To do this, we're going to add 6 electrons to the left-hand side of the equation. By adding in the 6 electrons to the left-hand side, that gives us a -6 charge to balance out the +12. So our total now on the left side is a +6. This now balances with the +6 we have on the right side of the equation. That completes adding electrons to balance the charge with each half reaction. Our next step is to now balance the charge between the 2 separate half reactions. What this means is we have to make sure we have the same number of electrons being gained in reduction as we have being lost in oxidation. We can see reduction has 6 electrons coming in, but the oxidation has only 2 electrons being lost. What we need to do then is take the oxidation half reaction and multiply the whole reaction by 3 so that we have 6 electrons being lost just as we have 6 electrons being gained, to balance and make sure the charge being gained and lost is the same in the 2 half reactions. Once multiplying the oxidation half reaction by 3, we now have 6 electrons in the oxidation half reaction, which is the same as the 6 electrons in the reduction half reaction, and we're ready to move on to the next step of the strategy. The next step in the strategy, now that we've balanced the atoms being oxidized and reduced, we've balanced the oxygens, we've balanced the H atoms, and we've balanced the electrons, is to recombine the 2 half reactions back together into one overall oxidation-reduction reaction. We've now recombined the 2 half reactions into one overall reaction. Now, when we've done this, we can see we have 6 electrons on the left and 6 electrons on the right. The arrow in a chemical equation is similar to an equal sign in a math equation, so what we can do with the 6 electrons on both sides is eliminate these from the equation. This is why we wanted to balance the electrons before recombining the 2 half reactions. Eliminate the electrons on the right, eliminate the electrons on the left, and we now have what we believe to be our balanced redox equation for acidic conditions. A final step in balancing for acidic conditions is to inspect to see if there's anything we can simplify. For example, if we had water molecules on the right and water molecules on the left, if some can be reduced, that would simplify the equation. This equation has nothing that can be simplified, so this is our final version of our acidic conditions balancing. If a reaction indicates that we want to balance for basic conditions, we need to go through all the steps of balancing for acidic and then have a couple steps added on at the end, additional steps that are included for basic balancing. If a solution is basic, it has hydroxide ions. What we want to do is look at our acidic equation and identify how many H plus ions are present in this reaction. We then add to each side of the equation the number of hydroxide ions that's equal to the number of H plus ions. So the first step in balancing for basic, we identify how many H plus ions are present in the acidic balanced equation, and then we add a number of hydroxide equal to the number of H plus ions to both sides of the equation. Both to the left and the right, we've added in 14 hydroxide ions. The next step, we want to identify how many hydroxide ions and H plus ions combine on one side of the equation to make water molecules. We're going to combine these together and replace the separate 14 OH and 14 H plus ions with 14 water molecules. So now instead of seeing separate OH and H plus ions, we have 14 water molecules written into our equation. Our next step now, we want to eliminate any water molecules or simplify our equation. We can see we have 7 water molecules on the right side. We have 14 water molecules on the left. This can be simplified by taking the water molecules on the right, the 7 H2Os. These can be eliminated. On the left side, it can be changed from 14 water molecules to 7. This would now be our balanced equation for basic conditions, where we've gone through acidic and then added on 2 more additional steps at the end to balance the equation for basic conditions.